Alright, today we're going to be talking about how to do numerical systems, otherwise known as numeral systems. Before we get into the lecture, I want you to try understanding. What do you think this says? This is binary code and it outputs a certain string or text. Right? String is the same thing as text. So this binary code outputs a text. Alright, so basically what you just saw is the most recognized program in the world, in my opinion. It is the Hello World program. We teach this to all introductory students, and this is basically what you start off programming. Now, although I'm not going to be teaching you how to do text to binary and binary to text, it emphasizes a very important aspect about computers. Computers only understand machine language at the end of the day. We can use a high-level language such as Java because Java has human words, so that we personally can program computers to do what we want easily. But programs or the compilers that we utilize, right, that will convert the Java program, it will convert the high-level language into this 0 and 1 that we see, the binary code that we see on the screen right now, because computers can only understand 0 and 1, yes or no, good or bad, true or false. So basically they understand zeros and ones. So how do we convert between different numerical systems? Alright, so let's start off with the decimal system. The decimal system is the system that you've been utilizing ever since you were in preschool. Right, you might not have called it a decimal system. If you have, that is really cool. Props to your teacher. But basically, a decimal system is a base 10 system. Right, every number can be deconstructed in parts with k times 10 to the power 1. Now, that seems like a weird sort of equation, but let me explain. We can deconstruct literally any number, right, to the power of 10. So we can make it so that it's the sum of a bunch of numbers that are times 10 to the power of some number. So let's look at 53,627. All right, so 53,627. What's 10 to the power of 5? 10 to the power of 5 is 100,000. The best way I remember it is that whatever number we put in the top of 10. So if it's like 10 to the power of 5, there are 5 zeros. So 5 zeros would imply that it's 100,000. So does 100,000 fit in 53,627? I don't think so. Right? So we subtract 1. So we do 10 to the power of 4. 10 to the power of 4 is 10,000. So can we fit 10,000? Yes, we can actually. We can actually fit multiple 10,000s within 53,627. So how many? Well, we look at this digit, right? 5. Because we really can't like fit we can fit three 10,000s within our entire number. However, are we really maximizing that number? So we have to realize that we can fit 5 10,000s within 53,627. So we rewrite it as 5 times 10 to the power of 4, right? 5 times 10,000. All right, so now we subtract 1 again. 10 to the power of 3. What is 10 to the power of 3? 10 to the power of 3 is 1,000. So how many 1,000s after subtracting 50,000? So we're not looking at the 50,000 anymore. We have 3,000 now, 3,627. Right? So how many 1,000s can we fit? Well, we can fit 3 1,000. So we can rewrite that as 3 times 10 to the power of 3. So we have 5 times 10 to the power of 4, which can be emphasized to 50,000. We could do 3 times 10 to the power of 3, which is 3,000. All right, now we do it again. So 10 to the power of 2. 10 to the power of 2 is 100. How many 100s can we fit after removing 53,000? All right, so we have 627 remaining. 600, I think we can fit around 6 100s within 627. So we do 6 times 10 to the power of 2, 6 times 100, so 600. So we have 50,000 plus 3,000 plus 600. So we're at 53,600. We do it again. 10 to the power of 1. 10 to the power of 1 is, you guessed it, 10. So we do, how many 10s can we fit in 27, the number that's remaining? Well, we could fit 2 10s within 27. So we rewrite that as 2. right? So when we do 2 times 10 to the power of 1, we get 20. So we're at 53,620. All right, and the last system that we have is 10 to the power of 0. 10 to the power of 0, or any number to the power of 0, is 1. All right, so how many 1s fit into 7? Well, 7. So we rewrite that as 7 times 10 to the power of 0, otherwise denoted as 7 times 10 to the power, 7 times 1. So we add all these numbers together. 5 times 10 to the power of 4, 50,000. 3 times 10 to the power of 3, 3,000. 6 times 10 to the power of 2, 600. 2 times 10 to the power of 1, 20. 7 times 10 to the power of 0, 7. And then we get 53,627. Alright, so why did we do all the work? Really, what I was trying to show you is that we can decompose every number so that it's actually a sum of some constant times 10 to the power of some number. Alright, this is going to be especially important when we're doing other base systems. So it looks really weird when we're doing decimal systems because we're so used to decimal systems and it's using a basic number such as 10. However, when we go into binary, we actually have a different base that we have. We have base 2. So we have some binary code. 1011 base 2. Base 2 emphasizes that this is not your regular number. This isn't decimal. This isn't the number that we're used to, right? This is a computer number. 1011 base 2. And basically every number in this code represents some number to the power of 2. 2 to some number. Alright, so allow me to explain. This area is going to be called the 2 to the power of 0 range. So I have this table here, and I rewrote the binary code. So we have 1, 0, 1, 1. So the last number is 1. This means that there is one number, and in this case, it's going to be 2 to the power of 0. So every space here is going to be whether or not if it's 2 to some number. So we have 2 to the power of 0. Right, 2 to the power of 0. We have 1. So we do have 1 to the power of 0. We have 2 to the power of 1. That's equal to 2. And in our code, it says that we do have 2 to the power of 1. So we have 2. Now we have 2 to the power of 2, which is 4. Our code doesn't say that we have a 2 to the power of 2 because it says 0. In this case, we don't add the 4. So we added all the numbers that we had in our code. So we have 1 and 1. We have 11. So if say that we didn't have the 1, 0 here, right, we would add these together and we would get 3. That would be our regular number code. All right, but we have a 4-digit number in binary right now. So as we can see here, 2 to the power of 2, 4. We don't have a 4 in there, so we don't add it. All right. We do, however, have a 8 because we have a 1 in the place where it will be 2 to the power of 3. So 2 to the power of 3 is 8, and we have 1 8. So we add it. So we have 1 to the power. We have one number that has 2 to the power of 0. So we add 1. We have one number that is 2 to the power of 1, and that is 2. And we have one number that's 2 to the power of 3, which is 8. Right? We have 8 here. We add them together and we get 11. 11 is our base 10 decimal system. All right? So we basically just converted some binary number into decimal. All right? So to clear things up a little, we're going to do a practice problem. So we're going to convert our regular number, a base 10 number, into binary. So my first rule of thumb is so 2 to the power of what number can we fit into 46? So if we do 2 to the power of 6, what do we get? 2 to the power of 6, 64. 64 is too big and it cannot fit into 46. So we have to subtract 1. So what's 2 to the power of 5? 2 to the power of 5 is 32. I think we can fit a 32 within 46. So we do 46 subtract 32 and we get 14. All right, so 14 is the number that remains. So 2 to what number can we fit into 14? So we look at the next thing. 2 to the power 4 equals 16. 16 cannot fit into 14 because it's too big. So we put a 0 here, right? Because that is the 2 to the power 4 slot. We don't have a 2 to the power 4, so we don't have a 1 there. So there's no 1 here, right? It's a 0 because we can't fit a 16 here. So we look at the next best thing, 2 to the power 3, which is equal to 8. We can fit an 8 in here. So an 8 would go under 14. So what is 14 subtract 8? 14 subtract 8 equals 6. All right, so we add a 1 here because we can fit a 2 to the power 3. So we can put a 2 to the power 3 within the remainder that we get from 14. Remember, 2 to the power 5, we've already taken away 32. So 32 is already gone, so we are left with 14. And now, since we can't use 16 in there because it's too big, we use 8. And 1 8 can fit in there, so we get 6. All right, so we look at the next best thing, and we get 2 to the power of 2, which is equal to 4. 4 can fit into 6, so we subtract. 6 minus 4 is equal to 2, and we have a remainder of 2 left over. So now what do we do next? We do 2 to the power of 1, which is equal to 2. So 2 can fit into 2 because they're literally the same number. So we can fit 2 to the power of 1 within this remainder. All right, and we get 0, right? And basically that's how we convert the decimal system into binary, because now if you look at this, right, if we have a 0, we can't really fit a 1 within, 2 to the power of 0, which is equal to 1. We can't really fit a 1 within 0 because, well, it doesn't work. 0 is nothing and 1 is something. So we just leave a 0. We can't leave this blank, so I can't just skip this 0, right, and just leave it like this. All of a sudden, then it would shift it, right? So you have to make sure that everything is there. I can't just write 1, 1, 1, 1, 1, because that wouldn't make sense, right? Every single slot represents a number, right? A type of number or a deconstruction of that binary system. Right, so 0, the last 0 of the binary number represents something 2 to the power of 0. So if it doesn't have it, it's just going to be 0. But if it does have it, most likely if it's an odd number, right? So if it was like 47, right, we would have a remainder here. We would have a remainder of 1. In that case, then I would put the 1 here. Right, so that is our answer, 1 0 1 1 1 0. Do not forget the zeros. If you're unable to put a number within the remainder that we get from continuously doing this process, you have to put a 0 because then it does not shift the order of the binary code. Binary code has this set structure. Alright, so there are other numeric-based systems, octo, which is a base 10 system, and hexadecimal, which is a base 16 system. I'm going to be touching on hexadecimal pretty quickly. So hexadecimal can be rewritten as 0 to 9, but then after 0 to 9, we have to use the alphabet, A, B, C, D, E, and F. So in the best way I can utilize this hexadecimal or show you how this works is through another example. So I'm going to be converting a regular number, 1984, base 10. So a regular number, a number that you're used to. It's probably a year of someone that it's already the year of birth of someone you probably know. And we have to convert that into hexadecimal. All right, so my first range of thought is, so we know that 16 is a base 16. So we have to, instead of thinking about how many 2's can fit in there, how many 10's fit in there, we have to think how many of what number to the power of 16 will fit into 1984. So my first rule of thumb is try a pretty big, but not really big number. So 16 to the power of 3. So 16 to the power of 3 is 4,096. 4,096 is a pretty massive number. I don't think it would fit into 1984. And if we subtract 4,096 from 1984, we're going to get a negative number. So it doesn't work. We have 0. All right. 16 to the power of 2 is equal to 256. 256, I can think we can fit multiple times in 1984. So we divide 1984 by 256, and we get 7 point something something something. That means that we can fit a maximum of 7 256s within 1984. So 256 times 7 is equal to 1792. another year, probably another historical year. Anyway, 256 times 7. So if we do 256 times 8, we're probably going to go over 1984, and we do not want that. So we subtract 1984, our original number, subtract 1792, and we get a remainder of 212. Yes, another 256 wouldn't work because it would have been approximately 40 off. All right, so 212. Now my next rule is how many of 16s can we fit in there? So 16 to the power of 1, right? So we have to make sure we're going over or in order. So we have 16 to the power of 3, then 16 to the power of 2, then we have 16 to the power of 1, and then we're eventually going to hit 16 to the power of 0, which is, as you guessed it, 1, because any number to the power of 0 is 1. All right, so 212, we divide 212 by 16. We have to find out how many 16s can we fit within, how many 16s can we fit in 212. So we do 16 times 12. Well, when we do that division, so 212 divided by 16, and we get 12. So that fits perfectly. 16 times 12, 212. So when we subtract 212 from 212, we get 0. So we don't really need a remainder. So in this case, we would just leave this as 0. But if it was like, say, 5 as the remainder, then we would put 5 here. Another way of rewriting this would be in its constant form. So 7 is 7 times 16 squared, right? Plus 12 times 16 plus 0, since we don't have any remaining, is equal to 16 to the power of 0 is equal to 1984. So these represent our base 16, our base 16 to the power of 1, and our base 16 to the power of 2. And then these are our constants. This is what we're multiplying 16 to what number, and then we're adding them all together to get our decimal system. So we can rewrite that as 0, 7, 12, 0. However, there is no 12 in hexadecimal. And if there is, then it represents something completely different. We look back to our chart. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, and then D, E, and F. So what would we do in the case of 12? Well, in that case, we rewrite it as 0, 7, 12, 0, 2, 7, C, because A is equal to 10, B is equal to 11, C is equal to 12. So our answer to this question will be 7C0 base 16. All right, that wraps up our video for today. Thank you.